Okay, everybody. This is chapter 12. We are going to be talking about ANOVAs. And the long version of ANOVAs is analysis of variance. So after this lecture, hopefully you will be able to explain what an ANOVA is, how it works, what the purpose is. You'll be able to do an analysis of variance on data. You'll be able to compute eta squared to measure effect size of an ANOVA hypothesis test. You'll know when and why to do post hoc tests, and you'll be able to compute Tukey and Sheffy, although we're only going to use Tukey. So your book covers both. Okay, so a little introduction into analysis of variance. When we've been doing t-tests, hypothesis testing, right? Repeated measures or independent measures, t-testing, and that works fine when you're comparing two groups, right? Maybe two different treatment conditions or two groups of people. That works great. But what if you have multiple treatment groups? What happens if you have three, right? And so the problem, if you recall, when you're using a t-test to compare two groups, you do have a possibility of committing a type 1 error, right? And so in this first scenario up here with group A and group B, excuse me, let's go back here. If you set your alpha at 0.05, you'd have a 5% chance of committing a type 1 error. That would mean a 5% chance of rejecting the null when you really shouldn't reject the null, right? And we've decided that we accept that chance, right? The possibility at a 5% level of making a type 1 error. It's not too bad. But if you were comparing three groups or conditions, you'd have a 5% chance of committing a type 1 error when you compared group A and B. You'd have another 5% when you compared group B and C. You'd have another 5% when you compared group A with group C. And so you see that although you don't really just add them together, you wouldn't add 5 and 5 and 5. It's a little more complicated than that. But the point is that it definitely increases the probability of a type 1 error way beyond, excuse me, the 5% chance. And that is not so tolerable, right? 5% is not great, but it's okay. More than 5%, and we start to be a little bit unhappy about that. And so what can we do? We can do an analysis of variance, or an ANOVA, right? And so if you see where the name comes from, it's kind of a shortened version of analysis of variance, right? Very similar, same general concept as a t-test. You're going to use the ANOVA to evaluate the differences between treatments or between groups. And we are going to use sample data as a basis for drawing general conclusions about the population. So those ideas are exactly the same as we've been talking about with t-tests and with hypothesis testing. The difference with ANOVA is that you can use it to compare more than two treatments or two groups at the same time. And the advantage and the reason you can do that is that it doesn't increase the type 1 error that you would have if you did multiple t-tests. So if you're trying to compare more than two groups and you did more than one t-test, you would increase the possibility or probability of committing a type 1 error. And with ANOVAs, we don't do that. So that's great. In chapter 12 and in this lecture, we're going to be just talking about the simplest kind of ANOVAs. Just like different t-tests, there are different kinds of ANOVAs. And today we're going to be talking about the simplest or the most basic ANOVA. It's a one-way or single factor ANOVA. And it is also an independent measures design. So what does that mean? A one-way ANOVA or single factor ANOVA means we're going to be looking at one independent variable. And when we're talking about ANOVAs, we're going to call that independent variable a factor. So let me give you an example. Let's say, I'm trying to find the example that your textbook talks about just to be consistent there in case you have read the textbook. Let's say that you have 3 different types of treatment. And so that would be your factor or the independent variable. And then we refer to the groups or treatments that you're testing within that factor as levels of the factor. So let's say we are going to test 3 different treatments for anxiety. One of them is medication, one of them is talk therapy, and one of them is medication and talk therapy. And so our independent variable or our factor would be a treatment type. And each of those 3 different treatment types would be the levels. So medication would be 1 level, talk therapy would be a 2nd level, and the combination of both would be a 3rd level. So just to get some terminology here from the get-go. And then the ANOVAs we're going to be talking about tonight or in this lecture are also, like I said, independent measures designs. So that means there's a separate group of participants for each treatment condition. And you'll recall with t-tests that we did between group and within group designs, right? It's very similar with ANOVAs. You can have ANOVAs when you have the same people tested across all 3 treatments, or you can have ANOVAs where you have 2 separate groups of participants. So you have group A that's going to only receive the medication treatment level. And then you have group B, totally different set of people. They're going to receive the talk therapy level of treatment, right? And then you have a 3rd group, again, totally separate, no overlapping, brand new participants that are going to receive both medication and talk therapy. And so that's what we're looking at here. One independent variable or a single factor and independent measures design, meaning that there's separate groups of participants for each treatment condition. Just a preview for chapter 13. Chapter 13 is going to continue talking about ANOVAs, but it's going to be looking at single factor repeated measures designs. So single factor would mean that there's one independent variable, and the repeated measures part would mean that there are the same participants across all 3 treatments. So in that type of design, you'd be looking at one person or a group of people. Let's say our sample is 10 people. 10 people are going to receive medication maybe for a month. Then those same people would receive talk therapy for a month. And then those same people would receive the 3rd treatment level of talk therapy and medication. So that would be what a repeated measures design would look like. Another thing that's possible with ANOVAs is a 2-factor design where you'd have 2 independent variables. So let's say we wanted to look at treatment types for anxiety and age. So maybe that's our 2nd independent variable, and we would look at the 3 different treatment types that I've already talked about, but then we would also maybe have 3 different age groups. So we'd have adolescents, young adult, and older adult, let's say. And so it's possible with ANOVAs to look at more than one independent variable and more than 2 levels of each independent variable. And that example would be called a 2-factor or factorial design. So ANOVAs are really neat. There's a lot of things you can do with them. All that to say, we're going to start in this lecture with just the most basic ANOVA, the single factor independent measures design ANOVA. Okay, so here are a couple of examples. And let's, for practice, let's identify the factor and levels for each design or each example. So this first one, you're comparing three types of therapy: art, play, so art therapy, play therapy, and cognitive behavioral therapy for effectiveness in reducing anxiety in young children. So it's kind of what the example I was just talking about. Children are going to be randomly assigned to one therapy only, okay? So that's independent measures. They're not going to do all three. They're just going to be assigned to one type. So what is the factor here? The factor is the type of therapy, right? And the dependent variable that we'd be looking at, just for fun, is anxiety level, right? We're going to see how the type of therapy affects anxiety level. And the levels for that factor are art, play, and cognitive behavioral. So those will be the three levels. Let's do another one. So let's say you want to compare young, middle-aged, and older adults for memory ability. And you give them a list of words to remember, and after 5 minutes, count how many they can recall. So I'll give you just a minute before I jump in. What is the factor here? And what are the levels of the factor? So the factor is age, or like age range, you could say. And the levels are young, middle age, and older adults. And the third example, let's say we want to compare income for individuals with high school education, some college, college degree, and graduate degree. And so we're fundamentally asking with this research design, does it pay to go to college, right? How much do people make when they have some college versus a graduate degree, let's say? So what would be the factor and levels here? I'll give you just a minute again. So the factor is income, or excuse me, the factor is education, right? The factor is also known as the independent variable, and income would be the dependent variable in this case. The levels of our factor are high school education, some college, college degree, and graduate degree. So in this example, there are 4 levels of our single factor of education. So all of these examples are examples of single factor ANOVA designs. Okay, so let's talk about hypotheses in an ANOVA. As we've talked about before, under the null hypothesis, any differences in the sample means will be due to sampling error or random chance, right? So kind of phrased differently on this slide, do all samples come from the same population? In other words, is there no effect, right? If it's true that the samples all come from the same population, any difference that we observe in the sample means will be due to what? And I actually just told you at the beginning when I turned to this slide, again, in the null hypothesis, kind of across the board of all these different types of hypotheses testing that we're doing, t-tests, ANOVAs, etc., the null hypothesis means there's no effect, right? The independent variable doesn't do anything to the dependent variable. And to the extent that we observe differences between the sample means, just means that we're looking at sampling error or random chance, right? So there is going to be sampling error when we draw samples from populations, even when those populations are essentially the same, right? On the other hand, do the samples not all come from the same population? And in this case, I'm looking down here, the population mean differences due to the independent variable are causing systemic differences between the sample means. So in this case, the sample means are different, and they're not just different due to sampling error, they're significantly different, and it must be due to differences in the population means themselves, right? And we would conclude that there is an effect of the independent variable. So this is our null and alternate hypotheses, in an ANOVA. Just to go over this again, the level of the factor does not affect the dependent variable, right? Here's our null hypothesis, kind of phrased all different ways. In other words, the population means of the groups do not differ from each other. None of the group means significantly differ from any other group mean. So using our statistical notation, you'll see down at the very bottom here, our null hypothesis is that the mean for population 1 is exactly the same or equal to the mean of population 2, which is also equal to the mean of population 3. So in our example where we had 3 different treatments for anxiety, the null hypothesis would say those treatments don't have any effect. They're all coming from the same population. Treatment 1, 2, and 3 make no difference on the level of anxiety. Our other hypothesis, the alternate hypothesis for ANOVA, is that there is at least one mean difference among the populations. So at least one group mean significantly differs from at least one other group mean. And here, there's no simple statistical notation or mu equation like there is for the null hypothesis, right? Why? Why isn't there a simple equation? Well, because there are all kinds of ways that the null hypothesis can be wrong, right? It could be, just as one example, that all the means are different from every other mean. So perhaps, and that's what this is showing right here, perhaps one alternate hypothesis is that the mean for population 1 does not equal the mean for population 2, and it also does not equal the mean for population 3, that they're all different from each other. Another possible alternate hypothesis is that there are some means different from others, but other means do not differ from others. So just as one example, perhaps the mean for population 1 does equal the mean for population 3, but mean for population 2 is different from both 1 and 3. That's one possibility, right? Perhaps play therapy is different, but arts therapy and cognitive behavioral are both the same. So there are, as you can see, all kinds of different combinations or ways in which the null hypothesis could be wrong. And again, the null hypothesis just says that none of the group means significantly differ from any other group mean, that they're all equal. The alternate hypotheses, and there are many, is that at least one of them is different from at least one other one. And again, there's lots of different possibilities, and we'll come back to this concept toward the end of this lecture. But the key thing to remember for the alternate hypothesis is that at least one group mean significantly differs from at least one other group mean. Okay, so what do we do with that? How do we notate that statistically? We don't. There's no easy, clear statistical notation for the alternate hypothesis in an ANOVA. Again, what the alternate hypothesis predicts is at least one mean is different from the others. And notice, again, this doesn't tell us which mean is different from the others. When we get to toward the end of this lecture, we'll talk about the results of an ANOVA hypothesis test, and we will be able to conclude that we either reject the null hypothesis or we fail to reject the null hypothesis. And if we reject the null hypothesis, we won't know from the ANOVA which mean is different from the others, or if they're all different from each other. All we'll know is that at least one of them is different from the others. And another way of another term that people use to describe this is the omnibus test or overall test. It just means we're not going to get any specific information about which mean differs from which mean. All we're going to know is that when we're testing all these different means, 3 or more, one of them is different from another, at least one. So ANOVA is kind of an omnibus test or an overall test of whether or not the null hypothesis is true. Okay. So remember the test statistic for the independent samples t-test. T-test statistics are always about ratios, right? When we were calculating the t-test test statistics, we used this ratio, right? So the numerator had the difference between two sample means, right? So we would take two samples from either two groups or two treatment types or something like that, and we'd compare them. We'd subtract one from the other. And then in the denominator, we always had the standard error, which is another way of explaining or stating standard error is the difference expected with no treatment effect, due only to sampling error. So remember, with t-test, we looked at a distribution of sample means and a distribution of differences of sample means. And we said, what would be the difference we'd expect if there's actually no difference in the population means? But of course, through sampling, we do see a difference in these two sample means. What would be the difference we could expect with no treatment effect, just sampling error? And so that's what went into the denominator, right? It's the standard error, which is also the standard deviation on the distribution of differences of sample means. So hopefully you can use the pause, rewind, and play features on the video to listen to this a couple of times and let it sink in. Some of it's review. Hopefully most of this little section here is review, but I know that these are, when it's the first time you're hearing these concepts, it sounds a little wild or difficult to understand. So feel free to pause, stop, rewind, and listen again. And go to your book. They'll probably explain it a little bit differently, and hopefully one or the other will make sense to you. So the point I want to make here in this slide is that our test statistics were always ratios, right? And the ratio here is the obtained difference between two sample means and the standard error. So how do you find mean differences in ANOVA, right? So the clue is back in the name, ANOVA. Remember, ANOVA is analysis of variance. So that's the clue, right? When you have two means, you can just subtract one from the other, right? Mean 2, mean 1, 20 and 15. So just 20 minus 15 is 5. Very straightforward. But when you have three means, like let's say you have a mean of 15, you have a second mean, sample mean of 20, a third sample mean of 10, how much is the difference between the sample means? Do you just subtract one and then the other and then the other? Or do you subtract 1 from 3 and 1 from 2 and 2 from 3? Or what do you do here? So with ANOVA, because that's kind of complicated and there's no clear way to just subtract, instead of talking about the differences between a mean or means, we're going to talk about the variance of the three means, okay? And again, that's kind of the clue goes back to the name. We're going to be analyzing variance with an ANOVA. And the larger the variance, the more spread out the means are from each other, so the more different they are. So we're going to be looking at variance, which if you remember, we talked about very early on in the class. I don't know if it was chapter 1, but it was 1 or 2. It was pretty early on. We talked about the concept of variance. And we're going to return to that now. And we're going to be looking at the variance of these means. So 15, 20, and 10, what's the variance in those numbers? So the test statistic for an ANOVA is going to be F, F as in Frank. So not a T anymore. When we're doing ANOVAs, we're going to be looking at F. And there's a new distribution to go with that, right? Just like the T test statistic has its own distributions, F also has a distribution. And we'll look at it in this lecture and see kind of what it looks like. The F statistic is a ratio, just like the T test statistic, based on sample variances instead of sample mean differences. So again, instead of looking at what's the difference, the simple difference between two different means, we're going to be looking at the variance of 3 or more means. And otherwise, the ratio is pretty similar to the T statistic, right? In the numerator, we want a single number to measure the differences among all the sample means. We're going to be looking at variance between all the sample means. And in the denominator, we're going to be looking at a single number that measures the mean differences that we would expect if there's no treatment effect. So just like the denominator was standard error in the T test, similarly in the F test, we're looking at what variance would we expect if there's no treatment effect? If the variance was all due just to sampling error, what would the variance be? And that's what our denominator is in an ANOVA with an F test statistic. So let's talk about variance again. There are two major measures of variance that are involved in ANOVA testing. Between treatment variance and within treatment variance, right? So between treatment variance describes the variability that exists between treatments or measures, between treatments and measures the differences between the sample means. So up here, you've got treatment 1 are the white boxes, treatment 2 are the gray boxes on part A of this graphic here. The between treatment variance is the variance between the white boxes of treatment 1 and the gray boxes of treatment 2. What is the variance between those two treatments? The other major type of variance in ANOVA is within treatments variance. So there is going to be variability that exists within each treatment sample, right? So treatment A, let's say it's art therapy, not everyone is going to score the same on anxiety levels just because they're all getting art therapy, right? There's going to be some variance among the participants who are receiving art therapy. And let's say treatment 2 is play therapy. Same, right? Everyone who's getting the play therapy isn't going to score exactly the same on an anxiety measure. There's going to be a little bit of variance among those scores. And so within treatment variance is the variance or variability that exists within each treatment sample. And then again, the between treatment variance is what's the difference or variance from one treatment to another. Okay. Let's see, what else did I want to talk about on this slide? In A, the top part of this graphic, the difference between the treatments is relatively large and easy to see, right? We can see very clearly that with the white or treatment 1 is very different from treatment 2. There's a clear separation here. B, in this B section, the lower section of the graphic and the experiment B, it's extremely unclear, right? The means are different 4-point different, right? Mean 1 is 8, mean 2 is 12, which is the same as up here, mean 1 and mean 2. But there's so much within treatment variance down here that it's really hard to see. And the between treatment variance is kind of overwhelmed or obscured by the within treatment variance. Because the variance of treatment 1 is so great, and treatment 2 also, we can't really see clearly that there's between treatment variance. And you might want to come back to this graphic. Your textbook presents this graphic late in the chapter when it's going over again, some of the logic or underlying concepts of an ANOVA. And you'll see that our F ratio is calculated using these two kinds of variance. So this is an important conceptual thing to understand, the between treatment variance and the within treatment variance. Okay. Explaining a little bit more here. Between treatment variance, again, variability that exists between treatments and measures differences between sample means. And that results from differences in the treatment and error. So the between treatment variance, what that's saying is that variability that exists comes from two places. It can come from the difference in the treatments themselves. So it could be that treatment 1 really truly is different than treatment 2, right? Art and play therapy have different effects on anxiety. But also built into that variance is error. Okay, there's some sampling error that goes in there as well. The within treatment variance is variability that exists within each treatment sample, and it results only from error, right? This says individual scores are not the same within each sample due to random, unsystematic effects. And that makes sense, right? So when you're looking back at this graph here, when I was saying, let's say that the white boxes, treatment 1 is art therapy. Everyone who gets art therapy is not going to score the same on an anxiety measure. But to the extent that they're different, right, that participant 1's anxiety score is different than participant 2's anxiety score is just sampling error, right? It's not due to the difference between one treatment and another because they both get art therapy. So within treatment variance is due only to sampling error. When you have between treatment variance, so what's the difference between treatment 1 and treatment 2? That includes both. It includes sampling error, and it also includes any real true difference in the two treatments. And that's what this slide is saying. So again, use your stop, rewind, and replay feature if this is not making sense to you. Or go back, read the chapter or that section of the chapter, and then listen again and see if it can sink in. And feel free to ask me questions, send an email, and let me know if this particular slide is not making sense to you. So all of this is going to get us to our F ratio here. So this slide is showing you total variability partitioned into two components. So when you collect samples from 3 different groups of people who are receiving 3 different treatment types, let's say, you're going to have total variability in your whole experiment. And that variability is going to be comprised of between treatment variance and within treatment variance. And essentially, if you added them together, that would give you your total variability. So between treatment variance includes systematic treatment effects and random unsystematic factors. That's going to go in the numerator. So down here, F ratio is differences due to treatment effects and error. This is also known as between treatment variance. The denominator is the within treatment variance, which are the variance within treatments represents just the random unsystematic factors. So down here, just another way to visualize it, here's our F ratio. The numerator, again, is the between treatments variance. The denominator is the within treatments variance, okay? So between treatment variance, differences due to treatment effects and error. Within treatment variance, differences due to error only. Okay. So what does that mean for the F ratio? The F ratio, here again, is the same thing that was on the previous slide. Between treatment variance over or divided by within treatment variance. What are the potential sources of these differences in ratios? Let's consider two scenarios. When there are no systematic group differences, that is, when there's no treatment effects, what would happen? So let's say that art therapy and play therapy, not at all different, right? In reality, there's a little bit of sampling variance in the scores, but there's no treatment effect of art therapy or play therapy. They don't make any difference on anxiety scores. Then in your numerator, differences due to treatment effects would be 0, right? And then you'd also have error. So we'd have 0 plus error. The denominator, differences due to error, that would just be the same, right? Error. So when there are no systematic group differences, when there's no treatment effects, in other words, when the null is true, we would get an F value of 1, right? Because error divided by error, right? Something divided by itself, it equals 1. And we would determine that there is no evidence to suggest a treatment effect. In other words, we would fail to reject the null hypothesis if that were true. So what's going on in this slide is we're kind of learning about what are the concepts behind the math. How does the math in the F ratio relate to what it means, right? What's going on? And because the F ratio is made up of, in the numerator, differences due to treatment effects and error, and the denominator is differences due just to error, when there's no differences due to treatment effects, when that's 0, our F ratio or F value would come out to 1. And so that's important to remember. When we have an F value that's 1, then clearly there's no treatment effects. And we just have error divided by error. And that's why we're getting an F value of 1. And that means we can fail to reject the null hypothesis, right? The null hypothesis is that there's no treatment effect. Okay, now, this is a different scenario. If you look here, oh, excuse me. If the treatment really does have an effect, then what happens? So this is the other possibility, right? In this hypothesis test, one possibility is that there are no treatment effects, right? The null hypothesis. Another possibility is the alternate hypothesis, that the treatment does have an effect. And so in that case, our F ratio would be some large number, right? The differences due to treatment effects would be something. It wouldn't be 0. It'd be some large number plus error divided by error. Okay, so here, if you can do the math, F will be noticeably larger than 1. So let's say the differences due to treatment effects is 25, right? And the error is 2. If you do the math, 25 plus 2 divided by 2 is going to give you a value much larger than 1, right? And if that's the case, you would determine that there is evidence of a treatment effect, that there are systematic differences between the groups, and we would reject the null hypothesis. In an ANOVA, the denominator of the F ratio is called the error term. So this is just another terminology point. When we were calculating and talking about the T statistic, the denominator was called standard error. Very similar concept. In ANOVA, it's called the error term. It represents just the differences due to error. And so what we've talked about in these last couple slides, just to recap, are the two possibilities that would happen with hypothesis testing in an ANOVA, and both conceptually what that means and mathematically how that would be computed, or what that would mean in terms of numbers. All right, some more about the F ratio. If the null hypothesis is true, the size of the treatment effect is near zero, right? That's just what we were talking about. The differences due to treatment effect would be pretty much zero. And that would mean that F is very close to 1, because you'd have error divided by error. If the alternate hypothesis is true, then the size of treatment effect is more than 0. Hopefully it's a really big number, right? And F will be noticeably larger than 1. So something on this slide, I want you guys to make sure that you understand what this is talking about, that this makes sense to you. Don't just memorize it. I think it's important to understand why these statements are true, okay? And if you don't understand, then go back a few slides and listen and watch again, or review the textbook. Okay, couple learning check questions here. True, false. ANOVA allows researchers to compare several treatment conditions without conducting many or several hypothesis tests. I'll give you a minute to see if you can answer that. And that is true, right? The big advantage of an ANOVA is that several conditions or factors can be compared in one test. So we do not end up with an inflated type 1 error rate. Another true, false. If the null hypothesis is true, the F ratio for ANOVA is expected, on average, right, to be around 0. So we would expect the F to be 0 if the null hypothesis is true or false. That's what we were just talking about. Remember, the F ratio is in the numerator, differences due to treatment effect and error. In the denominator, it's error only. So if the null hypothesis is true, that means differences due to treatment effects is 0. There are no differences due to treatment effects, right? And so you end up with, mathematically, just error divided by error. And would that equal 1 or 0? So the answer here is false, right? If the null hypothesis is true, the F ratio will have a value near 1. So you can memorize that, but there's going to be a lot of memorization, and I think it's better or easier to really understand why this is the case, and that way you can just figure it out. Okay, so some more kind of terminology sort of things here. or some more about notations and formulas. Like it says here on the slide, half the battle with ANOVA is learning the notation and using the various formulas. So the notation is a little bit different. There's some new terms and new notations for an ANOVA that we haven't talked about before with t-tests. This is a good slide to, I don't know, highlight or star and come back to. Of course, it's also covered in your book. So K is the number of treatment conditions, the number of groups, or the levels of each factor. So if you look up here, I have an example here. Let's say that we've got a study or an experiment where we're looking at the independent value or independent variable or factor of sleep, amount of sleep. And we're looking at how that affects memory, let's say. And so our factor is amount of sleep, and the levels of each factor are no sleep, a medium amount of sleep, and a full sleep. So these people got no hours, these people maybe got 4 hours, and these people got 8 to 10, let's say. K is the number of treatment conditions. So different conditions, different levels, the number of groups. In this example, K equals 3, right? So we've got no sleep, medium sleep, and full sleep. There are 3 different groups or levels in this ANOVA. N is the number of scores in each treatment. So in the no sleep treatment, there are 3 scores. So N1 equals 3. That's lowercase n. I just want to point out. N2 also equals 3. There are 3 scores. And little n3 also equals 3. There are 3 scores. Uppercase N is equal to the number of scores in the entire study. So uppercase N should equal all the little n's added up, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. In this example, uppercase N, big N, equals 9. T is the total of scores for each treatment. So it's kind of like it goes with lowercase n, right? In treatment 1, there are 3 scores, and the total of the scores is 11. So T1 equals 11. T2, we're going to add up the scores for treatment group 2. So little n tells us there's 3 scores, and T2 will tell us what's the value of adding up those scores. So 1 plus 4 plus 11 gives us 16. So T2 is 16. T3, we're going to add up 10, 5, and 8 to get 23. You can also use sum of x for each treatment, right? So the sum of x for treatment 1 is T1. Now, G, big G, is the sum of all scores in the study. That kind of goes with big N, right? How many scores are in the entire study? G is the sum of all the scores in the entire study. The value, so adding up the actual scores. Not how many scores, but what are the scores, adding them all up. It's you could also think of it or call it the grand total, and it's the sum of t's, right? So if the sum of x's for each treatment gives us these t values, adding up all the t values gives us a g value. So g in this example equals 11 plus 16 plus 23, which come from right here, and g equals 50. So important to understand what these notations are, and you'll see we're going to do a couple examples. These are all values you'll need when you plug in the values to our ANOVA formulas. Okay, so let's work through an example as we learn how to calculate all of this. Nothing's too complicated. It's just there's a lot to keep track of. So let's just dive right in here. Suppose you're interested in determining whether certain situations produce different amounts of stress. The amount of the hormone corticosterone circulating in the blood is a good measure of how stressed a person is. So you randomly assign 15 students into 3 groups of 5 each. In one group, stress is measured immediately after returning from vacation. So that would be called low stress. In another, you're going to measure stress after being in class for a week, moderate stress. In the last group, stress is measured immediately before final exam week, or high, right? Or maybe in this case, we could say once classes went online, right? High stress. So what are the hypotheses? So just like in the t-test, ANOVA involves hypothesis testing. We've got a null and an alternate hypothesis. The null hypothesis is that mean 1 would equal mean 2 would equal mean 3. Population means, that is. So the null says there's no effect of stress. And so the low stress and the moderate stress and the high stress will all be essentially equal. The alternate hypothesis, remember, is that at least one group mean is different from the others. So don't know which one, or maybe all of them are, but at least one of them is different. First step to calculating an ANOVA, get some basic values that you'll need for formulas that you're going to work with later. So you're going to calculate the mean and sum of squares for each condition or level, and that's been done here. You're also going to want to calculate little n and t. Remember, those two go together for each of the conditions or levels. You're going to want to calculate the sum of x squared, which includes all of the scores. And you might ask yourself, why the heck do I want to do this? Trust me, you're going to need it later. So find G, find N, and find K. So these are all the things that you'll want to have ready. And once we calculate them, then we can just plug them right into ANOVA formulas down the road. So when you do these calculations, and you might want to do them by hand yourself and just check and make sure you see where they came from. I'm not going to do them by hand with you. I'm just going to show you the PowerPoint screen here. But the average, if you would calculate the average here, would be 4. The sum of squares would be 22. N1, so the little n for this first level is 5, right? That tells us how many scores do we have in this level. We have 5, and you'll notice that's the same for 2 and 3. We have 5 scores. Excuse me. T1 is the sum of the scores for this level. So if we simply add them up, you'll get 20. The sum of the scores for level 2, just add these up and you would get 40. And the sum of scores for level 3, adding these up, would give you 65. The sum of x squared. So remember to be careful here with our order of operations. It's not the sum of x and then squaring it, right? You have to take each score and square it and then add them up. So we're going to do the exponent first, then the adding. So 2 squared, 3 squared, 7 squared, 2 squared, and 6 squared. Add that all up, right? And same for medium and high. If you do that, you should get 1299. And again, pause this slide at some point and just check, go through and make sure that you know exactly how all of these numbers are derived and that you're getting the same thing, okay? If you're not, or you don't understand where a number is coming from, shoot me a quick email and let me know. So G, you'll recall G kind of goes with T, right? G is the grand total, you can think of it, of all the scores. And so we're gonna add T1, which we said is 20, T2, which is 40, and T3, which is 65. and get a G value of 125. Big N is little n plus little n plus little n. So the number of scores in the entire study, 15, right? And K is the number of conditions or the number of levels that we have. And so in this study, we have 3 levels of stress. So K is equal to 3, right? We have low, medium, and high. So again, pause this, do the calculations, make sure you're getting the same thing. If you're not, and you don't understand where something came from, let me know. Okay, so ultimately, what are we looking for here? We're going to start, now that we've done kind of the initial steps of calculating all those figures on that previous slide, let's start at the end, really. What we're going to be looking for to compute an F, which is similar to when we computed a T, is the between treatment variance divided by within treatment variance. So that's ultimately what we need. We need some figure for between treatment variance and some figure for within treatment variance. How do we get that? Remember that when we are looking for a sample variance, that was notated with little s squared, and little s squared is variance, sample variance, and that was equal to the sum of squares divided by degrees of freedom. So very important here. Maybe look back, I did, at chapter, maybe it's 2, I don't remember, but look back at the section that talks about variance. Variance is equal to the sum of squares divided by degrees of freedom. And so what we're going to be doing is computing a sum of squares and degrees of freedom value for the variance between and variance within. Okay, so we're going to break this down and try not to get lost. This is just one example. Your book goes through a couple of examples also. So if you want that practice, you can watch the lecture, look at the book, and there are more practice problems on MindTap, of course. So we're going to break this down. First, we're going to compute sum of squares and degrees of freedom for the total study. We're going to call that sum of squares total. And then we're going to break down the sum of squares total into sum of squares between and sum of squares within. And then we can use those sum of squares values to compute the variance, right? And once we have variance, we can calculate F. Okay, so for between treatments variance, we're going to need a variance for between treatments, which means we're going to need sum of squares between and degrees of freedom between treatments. And then for within treatments variance, the denominator of the F value, we're going to need variance within. And for that, we're going to need sum of squares within treatment and degrees of freedom within treatment. So lots of calculating we're going to need to be doing, right? Another way of looking at what we're going to do, the final goal for the ANOVA is an F value, right? That's our magic endpoint. We're going to get a number for F, and we're going to have a critical value for F, just like we did for T. And we're going to have F obtained, and we'll look and see whether we reject the null or not based on our F value. And where does this F value come from? It comes from here. Variance between treatments, variance within treatments. Let's break that down. Each variance in this F ratio is computed as sum of squares divided by degrees of freedom. So again, for the numerator, variance between treatments, we're going to have sum of squares between divided by degrees of freedom between. For variance within, we're going to have sum of squares within divided by degrees of freedom within. And then let's break it down even further. Where are we going to get sum of squares between, sum of squares within? We're going to look at the total variability analyzed into 2 components. So we're going to look at sum of squares total as between and within, And degrees of freedom total is, we're going to analyze that into the two components of degrees of freedom between and degrees of freedom within. Once we're done with the example, you might want to come back to these couple slides and look again at the big picture. I think it'll make more sense after we've gone through one example. Okay, so just mapping it out here again, the entire process of an ANOVA requires 9 calculations. Sounds like a lot, but again, there's nothing too complex other than just keeping track of all the different calculations. So we're not doing any crazy calculus here or anything like that. You have to compute 3 values for sum of squares. Got to compute sum of squares total, within, and between. Then we also have to do 9 calculations for degrees of freedom. We have to calculate degrees of freedom total, within, and between. Then we have to calculate the 2 variances using those sum of squares and degrees of freedom values. And then we're going to use those 2 variances to calculate our F value. So hopefully you see how it all builds into each other. Okay, let's break it down. Where are we getting the sum of squares? So we're doing this part, the 3 values for sum of squares. Sum of squares total is calculated using this formula right here. And if you remember, before looking at this formula and getting too completely freaked out and overwhelmed, sum of squares, there were at least 2 different sum of squares formulas that you could use when we first talked about sum of squares. You could use the definitional formula or the computational formula. And remember, the definitional formula kind of made more sense from a conceptual standpoint, but the computational formula was a little bit easier when there weren't whole numbers or when there was a lot of numbers. And they both give you the same result. So you can use whichever one you prefer. In this, for ANOVAs and for calculating sum of squares in ANOVAs, we're going to use the computational formula. And the sum of squares, here's on the right here, is the computational formula that you should be familiar with, right? This is the same one that we talked about when we talked about sum of squares the very first time. It's the sum of x squared, excuse me, which again, be careful, there's no parentheses here, so the exponent comes first. So that means you're going to take each score and square it, and then add up those squared values. So sum of x squared minus sum of x squared, and in this case, because there are parentheses, you'll add up the scores first and then square that number that you get through addition. So the sum of x squared divided by n. So this is the sum of squares formula. When we're looking at sum of squares total for ANOVA, they've just subbed in g for the sum of x, which, if you remember, g is exactly the sum of x, right? The big G in an ANOVA is just adding up the values of all the scores in the study. So this isn't anything new. They've just added the ANOVA notation for sum of x. And so what you can do is plug in the numbers that we've already calculated into this formula. So if you remember on that slide with the table with mean and sum of squares and G and K and N, you're just going to plug those numbers in. So we already calculated sum of x squared. We already know G. We'll just square it. And we already know N. And so we can calculate sum of squares total. For sum of squares between treatments, the formula is N times the sum of squares for the treatment means. And this is another way of calculating sum of squares between. And sum of squares within is the sum of squares inside of each treatment. So we're gonna go over these in an example, but I want to point out here, sum of squares within treatments is something we already calculated. I'm going to go back to that table real quick so you guys can see what I'm talking about. Oops, there it is. Here we have sum of squares 1, treatment level 1, sum of squares 2, 18, sum of squares 3, 14. So when we were doing the preparation work for our ANOVA in this stage, we already calculated those figures. Excuse me. And so you're just, for sum of squares within treatments, you're just simply going to add those up. So add the sum of squares for treatment level 1, treatment level 2, and treatment level 3. And then one way of computing sum of squares between is to take the total that you compute, subtract within that you compute, and you've got between. So that's one easy way to do it. You can also use this formula, and I encourage you to use this formula to check your work, okay? So you should be able to just plug in, we already know t squared divided by n, little n, minus g squared over big N, and you're going to add that up. I'm sorry, add up all the t squared over n minus g squared over n. You should be able to use this formula to compute sum of squares between treatments, and it should, when you add that value to the sum of squares within treatments, you should get the sum of squares total. So this is a good way to check. When I'm doing ANOVAs, I compute the total, I compute sum of squares within, and then I compute sum of squares between in 2 different ways so that I make sure that my math is all working out correctly, okay? If you add between and within and you don't get the total, then something's wrong, right? So there's a check built in there. Okay. Oh, sorry. The last thing I wanted to say about this, the sum of squares between treatments, if you want to understand a little bit more about this conceptually, or you're curious about this formula, you can look in your textbook, page 342, for more detail on sum of squares between treatments. Okay, now moving on to degrees of freedom. Now remember, I'm going to go back here. For the F, we need the variance. For variance, we need sum of squares and degrees of freedom. So we just talked about how we're getting the sum of squares. Now we need to talk about where we get degrees of freedom. Degrees of freedom total is simply big N minus 1, right? So that is really consistent with what we've talked about with degrees of freedom before, right? The total number of scores in the whole study minus 1. Now, within degrees of freedom within treatments, when we did sum of squares within treatments, we found the sum of squares for each treatment or level, and we added them up. And when we did that, each sum of squares has an n minus 1 degrees of freedom. So we'll just add those up, right? So you add up n minus 1. And that should, another way to do it, which should give you the same exact answer, is to use big N minus K. So whether you do this way, taking n minus 1 for each treatment group and then adding that up, or you do it this way where you take big N minus K, you should get the same number. And that is the degrees of freedom within treatment. And then the degrees of freedom between treatments, for this sum of squares, when we did the sum of squares between treatments, that measured variability for the set of treatments among the 3 different treatment groups. And so the degrees of freedom is the number of treatment groups minus 1. Again, your book goes into more detail. I don't want to go into too much detail here and be talking at you guys for a couple of hours. So that's all I'm going to say. Check out your textbook, or feel free to reach out to me if you want to understand more. If you're not understanding something, feel free to let me know. Essentially, both the sum of squares and the degrees of freedom for between treatments is looking at variability for the set of treatments, or the degrees of freedom among the three groups. So degrees of freedom is the number of groups or levels you have minus 1, right? So all of these degrees of freedom calculations involve minus 1, right? Um, just like the degrees of freedom that we've talked about before. Okay, so now we've got all the numbers we need, right? Here's our prep work again, the original table with the scores, the means, the sum of squares, the little n's, the t's for each level, and then sum of x squared, g, big N, and k. Here is our example problem or question again. Here's the null hypothesis and the alternate hypothesis. And then here we're going to create or put values into an ANOVA summary table. And this is just a handy way of keeping track of all the things we need to calculate. It's also a concise method for presenting ANOVA results. It helps organize and direct the analysis process. And it's convenient for checking computations. When you use SPSS to do ANOVAs in lab, you'll get an output that looks like this, that has these columns and rows and these values. You don't necessarily see this in a publication. When you publish results, you don't usually see this table, but it's a really good table to have and to use when you're doing these ANOVA calculations by hand. Again, it just helps you keep track of things and organize things. And hopefully all of the things on this table will be familiar, except for maybe MS. And MS stands for mean square. And why mean square? What is that coming from? If you remember, variance is the mean of the squared deviations, right? So way back when we talked about variance, we first tried just subtracting the mean from each score, right? The score minus the mean, the score minus the mean, and adding that up. And remember, that always equaled 0, right? And so instead of just subtracting the mean from each score, what we had to do was square that value, right? And that would avoid getting 0 as a variance figure. And so variance is the average of the squared deviation, or the mean of the squared deviations. And so MS is mean squared, right? That's just another way of saying it. Okay, so let's do some calculations. Sum of squares total. So this box right here. And from our formula, sum of squares total is sum of x squared minus g squared over n. Sum of x squared, and this is, I'm pulling these values straight from this table right here. This table and these calculations. So you might want to copy this somewhere else or write it down. I'm not going to, it's kind of awkward to flip back and forth a ton of times, but these are already computed. I'm not just pulling them out of thin air. I'm pulling them from that slide. So when you get ready to do this table, when you're ready to do this step, it's just a lot of knowing what formula to use and pulling the right numbers, okay? So sum of x squared from our table is 1299, g is 125, and n is 15. So we've got 1299 minus 125 squared over 15. 125 squared is 15,625. When you take that divided by 15, you get 1041.6. And 1299 minus that equals 257.33. So our sum of squares total, we're going to put it down here in this box, is 257.33. Now, let's calculate sum of squares within. Remember, the sum of squares is within is just adding the sum of squares inside each treatment. So there were sum of squares values. I am going to flip back. Here they are, right? The sum of squares within each level or within each treatment. 22, 18, and 14. So we're going to add those up. 22, 18, and 14, that should be a plus sign, excuse me, equals 54. So we're going to put that in our table down here. The within treatments sum of squares is 54. And then sum of squares between. So you're going to use the formula first. It's the sum of t squared over n minus g squared over n, little n and big N. So add up each t squared over little n. And again, this is coming straight from the table. We'll go back and look at where is the t and the n. Oops, excuse me. So here's t, t1 over n, t2 over n, t3 over n. So that's where t1 squared over that n, t1n, or n1, excuse me, t2 squared over little n2, t3 squared over n of 3, or the third treatment level, minus g, again g is 125, squared over big N is 15. So most important thing here, take a minute, make sure that you know where I pulled all these numbers from. And I'm adding these up because it says sum up all of the t's squared over n. When we are grading homework and exams, I'm not going to care so much if you make a math error down here. But if you put the wrong numbers in, that tells me you don't understand something. So make sure that at this first stage, you're getting this part right, okay? This is where I can give you a lot of credit, maybe even full credit, if you're pulling the right numbers and you've identified the t's and the n's and to add them up, and the g and the big N. If you don't necessarily get to the same 203.33 because you made a math error along the way, I don't really care about that. I care that you know which formula to use and that you pull the right numbers from all that prep work in your attempts to calculate the sum of squares between, okay? So when you do that, 20 squared is 400, 40 squared is 1600, 65 squared is 4225. When you do all the math here, you end up with 203.33. That goes here. Between treatments, sum of squares, 203.33. Now, remember I told you, as a way to double check your math, you should be able to add the between treatment sum of squares and the within treatment sum of squares, and it should equal your total sum of squares. If that isn't true, when you add these two together and you don't get this, something is wrong. I don't know where, you're gonna have to find it, but something is not right, okay? If you don't wanna bother with this calculation of sum of squares between, you wouldn't have to, but I think it's a good idea because that way you can check your math, right? Okay, so let's move on. Oh, here we go. Sum of squares total should equal sum of squares between plus sum of squares within. That's what I was just talking about. Okay, Now calculate and fill in the degrees of freedom. And this is just a reminder, I'll put this up here again, degrees of freedom total, degrees of freedom between, and within. So here I just put them all on one slide because these are pretty simple, straightforward. They don't involve a lot of calculations. Degrees of freedom total is big N minus 1. Big N is 15. That's, again, from that initial table. Minus 1 equals 14. So that goes in the box down here. Degrees of freedom total, 14. Degrees of freedom within is equal to N minus K. Right here. You could also take little n minus 1 for each level and add them up. You should get the same thing. And that would be 12 in this case. And then degrees of freedom between is K, or the number of levels, minus 1. We have 3 levels, right? No sleep, moderate, and high. Minus 1 is 2. So we put 2 right there. Okay, now we've got our sum of squares, we've got our degrees of freedom. Now we're going to fill in our mean squared value and the F value. And these lines and these boxes means there's nothing to compute here. So we're not going to compute anything or fill in anything in those 3 boxes. The mean square between is also known as the variance for between treatments. And the variance, or mean squared, is equal to sum of squares divided by degrees of freedom. So pretty easy here. We're going to take 203.33 divided by 2, and that will give us the mean squared for between. For within, same thing. Sum of squares within divided by degrees of freedom within gives us mean squared within. And then for F, we're going to just look at variance between divided by variance within, or same thing, mean squared between, mean squared within. So we're going to take this divided by this. So it gets a little bit easier. Sum of squares is maybe the hardest or the most intensive in terms of calculations. So when we put some numbers in here, sum of squares between 203.33 divided by 2, you get 101.67. Within is 54 divided by 12, you should get 4.5. And then when you calculate your F, we're going to do mean square between divided by mean square within. 101.66 divided by 4.5, you should get 22.59. So there's our F. So all that work to get to this magic number, 22.59. So right off the bat, ask yourself, what does that mean? Any thoughts? Okay. If you recall, what is the F value when the null hypothesis is true? And you should remember the treatment effects plus error over error, essentially. And if the treatment effect is 0, then F would equal 1. And this is quite a bit larger than 1. So without comparing it to an F critical value, I can already guess probably we're going to be rejecting the null hypothesis. That's just a guess. We're not going to stop there for sure, but just kind of letting you know of what that F value means. Okay, learning check. An ANOVA produces sum of squares total of 80 and sum of squared within 30. For this analysis, what would the sum of square between be? So is it one of those, or is there more information needed? I'll give you just a second to try to answer that on your own. Okay, and the answer is 50, right? Because sum of squares total should equal the sum of squares within plus sum of squares between. And remember, one way of calculating sum of squares between is to do exactly this. Have the total figure and the within figure and just subtract one from the other and you get between. Okay, oh, excuse me. So tips for the F ratio distribution. So we have an F value now, and just like with other hypothesis testing, just like with the t-test hypothesis testing we did, we have to compare our F obtained with an F critical value, right? We have, in deciding whether to reject or failing to reject the null, we have to decide, is our F value in the critical region or not? And remember, if the null hypothesis is true, F will be around 1, and our F is like 22 point something. Because F ratios are computed from two variances, they are always positive numbers. Okay, there's never going to be a negative variance. F is equal to between over within variance, right? Between treatment variance over within treatment variance. Neither of those figures is going to be negative, so it would be impossible to have a negative F value. If you ever have a negative F value, something has gone very wrong. It is not possible. When you're looking up an F critical value, you're going to look in the table in the back of the book, just like with the T. And in the table, you're going to need to know 2 degrees of freedom values. There's the degrees of freedom numerator and the degrees of freedom denominator. Let me show you what that looks like. So here is just a piece of the table from the back of your book. And you do have to know 2 degrees of freedom, right? Here across the top, the columns are the degrees of freedom from the numerator. And then along the side on the rows going across are the degrees of freedom from the denominator. So kind of a pain because you got to know 2 different degrees of freedom values, but you don't have to worry about one-tailed or two-tailed tests, right? F is always a one-tailed test because it can't be negative. And you'll notice the F distribution is kind of an asymmetrical distribution, right? The F values are going to congregate here right around 1, right? When you reject the null, or when you fail to reject the null hypothesis, when the null hypothesis is true, F should equal 1. So the mode of an F distribution is 1. And then you'll get a tail going out to F values that are higher and higher. And then here's a representation of where the F critical is. And if the F obtained is in that gray shaded area, then you reject the null. So another thing to note about this table is that, let's say you're looking at the value F critical for 2 and 2 degrees of freedom. That's right here. The regular font value represents alpha 0.05, and the bold value, 99, represents F critical with an alpha of 0.01. So just like with t-test hypothesis testing, you want to know what your alpha value is before you look up the F critical, whether you want alpha to be set at 0.05 or 0.01. And degrees of freedom numerator is degrees of freedom for between. Degrees of freedom denominator is degrees of freedom for within. We already have those figures, so no new calculations. You just need to remember to pull the right numbers. In our example, the degrees of freedom in the numerator was 2, or the between degrees of freedom was 2, and the within degrees of freedom was 12. And so we'll look here for 2 and 12, and an alpha of 0.05, our F critical is 3.88. And even looking at alpha 0.01, our F critical is 6.93. If you remember, our F obtained was 22. So ding, 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 we can reject the null. This is kind of what I just talked about a minute ago, looking a little more at the F distribution. An F distribution, just like T and Z, is a distribution of F ratios under the null hypothesis. So this is like someone computing F values over and over and over and over again, and creating a distribution of what you get when you do a sample and you calculate an F value. When the null is true, most of the time you'll get an F ratio that's 1 or really close to 1. And then if you'll see this, the F values get larger and larger, and there's a tail on the right hand side here of the distribution. So positive skew. The F distribution is shaped slightly differently depending on the degrees of freedom, just like the T distribution. So this is kind of the general shape of it, but it will be slightly different. That's why you need the degrees of freedom numbers to look up the values for F critical. And here I've just shown you 0.05 alpha level. In this example, the F value, F critical was 3.088, and alpha 0.01, F critical is 6.93. Okay, so what's our conclusion? I already told you, but the F value we obtained is in the critical region for alpha equals 0.05. Remember, F critical, alpha 0.05 is 3.88. Our F value is way over here, 22.59. And so we reject the null hypothesis very clearly. This is how it would be written up in a journal or a report. F with degrees of freedom 2 and 12 equals 22.59. P is less than 0.05. So, does this result give us the whole picture? Remember, way at the beginning of this lecture, that is now quite long, our omnibus test, which is another way of saying our F ratio or F value, all it tells us, now that we've rejected the null hypothesis, is that at least one population mean is different from one of the others. But remember, I told you, it doesn't tell us specifically which means are different from other means. We just know that they're not all the same. And so more information is needed, I'm sorry to say. So what are we going to do? We're going to do post hoc tests. Post hoc tests are follow-up tests that are used to determine which mean differences are significant. So just to review, ANOVA compares all the individual mean differences simultaneously in one test, and a significant F ratio indicates that at least one difference in means is statistically significant. So all we know is that at least one of them is different from at least one other. That's all we know. They could all be different, or maybe just one of them is different, but we don't know which. And so again, we're going to need to do a post hoc test to figure out which ones are different. And it could be, here's our examples from the beginning of this lecture. It could be that they're all different. Mean 1 does not equal mean 2, does not equal mean 3. Another possibility is that mean 1 is equal to mean 3, but mean 2 is different from the others. And so what we're going to be doing with the post hoc test is to figure out what is different. And these are just two possibilities. There are many possibilities. Post hoc tests compare two individual means at a time, which is also called a pairwise comparison. So it will compare group 1 and 2, group 2 and 3, and group 1 and 3. And remember, each of those comparisons includes a risk of a type 1 error, which is called a test-wise alpha, and that accumulates with each comparison. And accumulating would give you an experiment-wise alpha. So when you do one test to see whether or not group 1 is the same or different from the group 2 mean, that's a test-wise alpha of, let's say, 0.05. But then when you have another test-wise alpha for comparing group 2 and 3, and another alpha for comparing group 1 and 3, all of those are going to accumulate and give you an experiment-wise alpha. That means an alpha that is over the whole experiment. And remember, so in other words, each pairwise comparison is kind of like a mini hypothesis test. And increasing the number of hypothesis tests increases the probability of a type 1 error, right? And we are not comfortable increasing the probability of a type 1 error. Just to review, type 1 error is a false positive. It's finding a result where one does not actually exist. It's deciding to reject the null hypothesis when the null hypothesis is in fact true. And so a high alpha is bad, right? We don't want to inflate an alpha beyond 5%. 5% we've decided we're okay with, we'll accept that, but we don't want to go beyond 5%. So remember, this was the whole reason we did an ANOVA in the first place, was because we didn't want to do 3 different t-tests and have a huge alpha. And so ANOVA evaluates all the mean differences simultaneously in one test. So our alpha stays at 0.05, and that's good. But the post hoc tests, or post test, use special methods to try and minimize the experiment-wise type 1 error rate. And what are these special methods? What does it do? There are 2 common options for post hoc tests. Tukey's, honestly, significant difference. This is mainly known as the Tukey's test, or Tukey's HSD, and the Sheffey test. We're not going to talk about that one. I think Tukey is used more frequently. Your book does talk about both, so you can look in your textbook to learn a little bit more about the Sheffey test. Tukey's uses a single value to determine the minimum difference between treatment means that is necessary to have statistical significance. So read that again and make sure you understand. So Tukey's calculates this value, this HSD value, and down here I've given you the formula for how to calculate it. And you get a number. And in order for the 2 group mean differences to be significant, they have to be greater than or equal to that number. Okay, and it is absolute value, so it can be negative. So again, this might make a little more sense when we look at an example, a concrete example. But this is really cool, right? Tukey has come up with something really useful. Okay, so we want to calculate HSD, or Tukey's. Where do we get all these values? Q comes from yet another table. We'll look at that in a second. The mean squared within comes from the ANOVA, right? The table that we did to calculate mean squares and F's and keep everything all organized. So we already have that value. We can just look it up. And then N is the number of people in each group. A side note about that. Unfortunately, Tukey's HSD requires us to have an equal number of people in each group. There is a way if you have unequal sample sizes. So let's say the people who did art therapy, did 10 people, and then the people who did play therapy ended up only being 9 people. That's no good for Tukey's test, but there is a way that the computer can work around that. So we're not going to do that by hand. That would be really involved, but just know that the computer can work around that. Okay, so let's figure out the Q value for the previous example. And to find Q, you need to know K and degrees of freedom within, which we do, right? We already know K is 3. That's the levels of treatment, or the levels of the factor in the study. And the degrees of freedom within, we know from our ANOVA table, is 12. So no new information or computations, just looking up a Q value and plugging it into the formula. So here's really similar to the F critical, where up here you're going to find your K value, and we said it was 3. And over here you're going to know degrees of freedom for the error term, or degrees of freedom for within, and we said that was 12. So when you highlight this 3 column, K equals 3, degrees of freedom within equals 12. Here are the magic Q values for whether, depending on whether you want 0.05 or 0.01. So let's say we're going to use 0.05 as our cutoff or our critical value. So Q equals 3.77 from the table. MS within from our ANOVA table is 4.5, and N equals 5. 5 participants in each treatment. Remember, they have to all have the same N. So we're going to plug values into the Tukey HSD formula to find which groups are significantly different from the others. So I'm sorry here. So 3.77 is Q divided by the square root of 4.5, MS within is 4.5, divided by 5, N is 5. And if you do the math, 3.77 divided by a square root of 0.9. 3.77 times 0.949, and you get 3.58. So our HSD value is 3.58. And then remember, the interpretation of that is that any two means have to have a difference of 3.58 to be considered statistically significantly different at an alpha value of 0.05. So looking back at our means, mean 1, the mean for that first treatment level is 4, and the mean for the second level is 8. 4 minus 8, negative 4. That's greater than 3.58. And remember, we're just looking at absolute value. It's okay to have negatives. Mean 1 minus mean 3 is equal to 9, negative 9. That's also greater than 3.58. And mean 2 minus mean 3 is negative 5, which again is greater than 3.58. And so how would you write that up? All of it, the ANOVA and the post hoc Tukey test. You'd say we are rejecting the null hypothesis with an F value of 22.59, and here 2 and 12 are the degrees of freedom for between and within, with a P of less than 0.05. The omnibus ANOVA revealed that type of situation does affect amount of corticosterone in the blood. Or was it? Oh, right, this was back to our stress example. Tukey's post hoc test revealed that the low stress condition, which is mean of 4, produced significantly less corticosterone in the blood than both the medium stress condition, which was an M equals mean of 8, and the high stress condition, which was an M equals a mean, of 13. And in addition, the medium stress condition produced significantly less than the high stress condition. So this is all saying that first we did a hypothesis test, right? We found that we would reject the null because here's our F value. And then we did post-hoc tests and found that all of the means are different from each other. So mean 1 and mean 2 are different. Mean 1 is also different than mean 3. And mean 2 is different from mean 3. So this is not the only way that you would write it up, but it's one way you could write it up. Okay, one last important thing here, effect size. So remember we talked about effect size with t-test, and we said that a t-test might yield a significant t-value, and you might decide to reject the null and decide that the two groups or populations are different, but we don't know how different, right? And R squared was one measure of effect size with t-testing, and R squared told us what proportion of variability in the dependent variable was accounted for by the treatment, or independent variable. With ANOVAs, it's same exact idea, except it's eta squared, not R squared. And eta squared tells us the proportion of variability in a dependent variable that is accounted for by the treatment, or by the factor, or the independent variable, right? And eta squared as a formula is sum of squares between divided by sum of squares total, which, if you remember, kind of represents the variance due to treatment. Sum of squares between is just the variance due to treatment divided by the total variance. So this should make sense to you then, why this formula represents the proportion of variability that's accounted for by the treatment, right? What proportion of total variance is due to the treatment itself? And again, we have those numbers. So calculating effect size of eta squared is pretty straightforward. You're going to plug in sum of squares between, which here's our ANOVA table, 203.33, divided by sum of squares total, 257.33. And when you do that calculation, you get 0.79. Okay, that's really it. Some basic assumptions of ANOVA. The observations within each sample must be independent. This is for the independent measures ANOVA. Remember we talked about in the very beginning, ANOVAs can use separate groups, independent groups of participants, or you can do repeated measures where you're using the same participants over several factors. When you're doing an independent measures ANOVA, the observations within each sample must be independent. The population from which the samples are selected must be normal. That's nothing new, it's kind of same that we've always talked about. And the populations from which the samples are selected must have equal variances. That's also called homogeneity of variance. Oops, excuse me. And violating the assumption of homogeneity of variance risks invalid test results. This is kind of showing you variance. So variance population 1 should equal variance population 2 should equal the variance of population 3. Variance here for the population. We're not going to go into any more detail on that. There are some ways in which SPSS can help you assess or check for homogeneity of variance. And there's, beyond the scope of this class, there are ways that SPSS can correct for if the violating this assumption. So if the variances are not equal, there are some ways around that. But again, way beyond the scope of this class. Okay, some quick learning checks. Which combination of factors is most likely to produce a large value for the F ratio? So When you're answering this, remind yourself what the F ratio, what it is, what two values are used to compute the F ratio. I'll give you just a minute. So the answer is B, large mean differences and small sample variances. So we want, remember the F ratio is between treatment variance divided by within treatment variance. So if there are large differences between the two treatment means, then our numerator would be large. And if there's small sample variances, if there are small within treatment variances, then our denominator would be small, and that would give us a large F value. If this is not making sense to you, go back and watch the first part of this lecture. You can also look at pages 357 to 360, and it talks more about this. And it also has some graphics to kind of emphasize these concepts. Okay, true or false? Post hoc tests are needed if the decision from an analysis of variance is failed to reject the null. So let's say you do an ANOVA, you get your F value, you look up your F critical, and you decide, nope, we are not going to reject the null hypothesis in this case. Would you still need to do post hoc tests? Yes or no? And the answer is no, false, right? Post hoc tests are needed only if you reject the null hypothesis. And remember, when you do an ANOVA, if you reject the null, what you know is that something is different. At least one of the means is different from the other one, but you don't know which one. Post hoc tests will tell you which one. If you've decided that the means are not different, then you don't need to do any post hoc tests because you don't need to know which ones because none of them are different, right? So hopefully that makes sense to you guys. True, false. A report shows ANOVA results of F, degrees of freedom 2 and 27 equals 5.36 with a p-value of less than 0.05. You can conclude that the study used a total of 30 participants. Oh, tricky, right? So to answer this question, you're going to need to know what those degrees of freedom represent, right? So we know the degrees of freedom that it's reporting are 2 and 27. And is this true or false? Give it just a minute here. And this is true, okay? So the degrees of freedom between, which is that first value, is the number of treatments minus 1. So the number of treatments minus 1 equals 2, because that reporting said degrees of freedom between is 2 and within is 27. So K must equal 3. That's what we can figure out from this reporting. And then degrees of freedom within is the total number of subjects minus the number of treatments. And we know from this report that that number is equal to 27. So if we work backwards, 27, n minus 3 equals 27, so the n must be 30. Bingo, right? Here's our number, total number of people in our sample, or total number of scores. This is just nothing fancy here that I'm doing, just some basic algebra. So knowing that when you report an F value, you're going to report the degrees of freedom between, and then comma, the degrees of freedom within. And then working backwards, knowing what those formulas are. The degrees of freedom between formula is K minus 1. The degrees of freedom within formula is N minus K. And so when we use those formulas and plug in these two numbers we were given, we can figure some things out, including the big N, okay? All right, so practice, practice a bunch. On MindTap, I'll also put some things on D2L for you to practice ANOVAs. Email me with questions. Okay, I forgot until now our extra credit quiz question for this. And I'm sorry, I didn't intentionally put it at the end. I just got so carried away with all of this ANOVA fun. So it's, let's see, it's around Easter time. My favorite Easter candy. Tricky, this is really hard. I like candy. Cadbury eggs, no. Those weird chocolate eggs with the toy inside. I think they're like Kinder somethings. No. I like caramel chocolate eggs a lot, but I gotta say my favorite Easter candy is chocolate peanut butter eggs. Chocolate peanut butter eggs. Okay, I hope you guys are all enjoying some Easter candy of your own, and thanks for watching. Stay well, and we will talk again soon.